This video is going to be going through the easy questions on work, energy and power. So use the video to check your work or to help you if you get stuck on any questions. So question 1A is to state the principle of conservation of energy. It's a 2-mark question. So for the first mark, you need to say energy cannot be created or destroyed. For the second mark, it can only be transferred from one form to another. Question 1B. A girl of mass of 45 kilograms is bouncing on a trampoline, as shown in the figure. State the form of energy stored due to the surface of the trampoline being stretched, and that's elastic strain energy or elastic potential energy. Question 1C. When the girl's feet lose contact with the surface of the trampoline, she travels upwards with a speed of 5.5 meters per second. First of all, we've got to calculate the kinetic energy of the girl as she leaves the trampoline. So that's part I. So our equation for kinetic energy is half times m times v squared. So if we pop our numbers in, half times 45 times 5.5 squared, we get a kinetic energy that is equal to 618.625 joules. And for the second part, calculate the maximum possible distance she can travel upwards after her feet has left the trampoline. So what we're presuming here is that all of this kinetic energy is going to be converted into gravitational potential energy. And our equation for GP is mg delta h. So what we're going to do is we're going to take our energy that we got from the last one and make it equal to this equation and then rearrange to see what we get. So we've got 680.625. That's going to be equal to her mass times the gravity times what we're working out. So that's her change in height. If we rearrange that, we get delta H is equal to 680.625 divided by 45 times 9.81. Type that into our calculator and you get a height of 1.54 meters. Moving on to question 1D. In reality, she does not travel the maximum distance that we just calculated. First of all, we've got to say, is she going to travel more or less than that? So in reality, she's not going to travel quite that high. The reason for that, first point, is not all of her kinetic energy is going to convert to the gravitational potential energy. So not all that kinetic energy is going to give her the height. What's going to happen is there's going to be some work done against the drag, the friction, the air resistance, and that's going to cause some of the KE to convert to thermal energy, which in this case is a wasted energy for the system. Question 2A, define the following terms, power and efficiency. So power is the rate of doing work, or we could say it's the rate of energy transfer by a system. And efficiency is the ratio of the useful power output of a system compared to its total input power. And I pop the equation there as well. So we can also do it with energy instead of power, but you do the useful power divided by the input power, and then we usually times it by 100 and give it as a percentage. Question 2B, solar panels can convert light energy into electrical energy. With no clouds, 5.2 times 10 to the 8 joules of energy are collected each day. Calculate the total power input from the sun's light energy. On the previous page, we defined power as the rate of energy transfer. So that's energy divided by time. So our energy is there, our 5.2 times 10 to the 8. Our time we're going to do in seconds. So there's 24 hours in a day. We times it by 60 because that's how many minutes there are in an hour. And then finally we times it by another 60 because that's how many seconds there are in a minute. So if we type all of this into our calculator, we are going to get 6,020 watts. So watt is our unit for power. That answer is actually rounded to the nearest 3 significant figures. The exact answer you would have gotten is 6,018.5 watts. Going on to the next question, 2C. Each solar panel is 20% efficient at converting the light energy into electrical energy. Calculate the power output each day. So efficiency is equal to our useful divided by our total or input times 100 to make it into a percentage. So what we've got is 20%, our efficiency, is equal to our useful output, which we're working out, divided by our total input, which is from our previous question, times 100. So the first thing that I would do is divide both sides by 100. So you'll get 0.2 is equal to our useful divided by 6018.5. And that means our useful energy is equal to 0.2 times 6.085. And you would get 1203.7 watts of energy produced. Question 2D. A family require 8.5 kilowatts of electricity per day. How many solar panels should they install to meet their needs? So the amount of power that they need each day, so I'll call that power PN, power needed, is 8,500 watts every single day. So I've times it by 1,000 because this is kilowatts and I want it in just standard watts. And what they are actually doing, so I'll put PO, so for power output, what they're currently producing from our previous question was 1,203.7 watts. So to work out how many we're going to do PN, the amount needed, divided by PO. So you're going to do 8,500 divided by our 1,200 to work out how many, and you get 7.06 solar panels. So obviously we're not going to be installing 7.06 of a solar panel, so we'll say 8 needed, round it up so they get extra power. Question 3A. A rescue helicopter is used to winch a casualty of mass 65 and a winchman of mass 80 kilograms, a vertical distance of 40 meters as shown below. Part A, calculate the combined weight. So first thing I'll do is work out the combined mass, 65 plus 80, that's 145 kilograms. And then to work out its weight, we're going to do mass times gravity. So we'll take that 145 kilograms, times it by 9.81, and you should get 1,422.45 newtons. So roughly 1,420 newtons. Part 3B, calculate the work done. Move it up so we've got some space. So for work done, we're just going to use force times distance. So we're going to take our answer from before, 1422.45, and times it by the 40 meters that it travels up, and you should get 56898 joules. So that's roughly 56900 joules. Question 3C. The average power output of the winch motor during the rescue is 320 kilowatts. Calculate how long it takes to raise the casualty and the winchman 40 meters. So let's state what we've got first of all. Our power from the question is 320 kilowatts, or 320,000 watts. From the previous question, we've got the work done, which was 56898 joules. So if we use our formula sheet, we're going to be using the equation. Power is equal to the change in work done divided by time. So you've also seen it in the other form, energy over time. Energy and work done are basically the same thing. We're going to rearrange this to get time. So we're going to do the change in the work done divided by the power. So we're going to do 56898 divided by 320,000, and you're going to get 0.178 seconds. So time is 0.178 seconds. Question 3D. The winch motor is 70% efficient. Calculate the average power input to the winch during the rescue. So our equation for efficiency, if you've forgotten, is going to be our total output divided by our input times 100 to make it into a percentage. So we've got 70% is equal to our output, which we have from the question above, our 320,000, divided by our input times 100. So if we rearrange that, we're going to get our input, which is our unknown, is equal to our 2,000 divided by 0.7. I divided that side by 100 already. And what you're going to get is 457,143 watts. So that is roughly 457 kilowatts. Question 4a. A skier of mass 70 kilograms moves down a slope between A and C, shown in the figure. They start at A, ski down to B, and then they travel a vertical distance of h. At point B, they continue along the horizontal until they come to rest. The skier loses 90 kilojoules of gravitational potential energy between A and B. Part A showed that the height of the ski slope h is about 130 meters. So our equation for gravitational potential is mg delta h, mass times the gravity times the change in height. And we know from the question here that our GPE that is lost is 90,000, because it's kilojoules, so 90,000 joules, and that's equal to the mass, which is in the question here, 70, times 9.81 times our delta H, which is what we're going to be working out. So we're going to rearrange this equation by doing 90,000 divided by 70 times 9.81. And when you type that into your calculator, you will get 131.1 meters. So that is roughly 130 meters. Question 4b. The skier travels a distance of 500 meters between A and B in figure 1. Figure 2 shows the variation of frictional forces as they descend between A and B. Use the figure to show the work done is about 20,000 joules. So the work done is equal to the force times the distance. That's an equation we know. And what you should also know is that the area under this graph, because it's a friction force, it's a force distance graph, that's the important bit. So the area under this graph is going to be equal to the force. So to do the area of a triangle, you do the base, so that's 200, times the height, 50, divided by 2, because it's only half of the space that is under the graph. This bit over here is not part of it. And then we're going to add it to the area here. And the area, the base here is 300, because it's going to be 500, take away 200. So we got 300 times the height, which is 50, and I'll put that in brackets. So if we type that into our calculator, you will get 20,000 joules. Question 4c. Use your answer to part B to calculate the kinetic energy of the skier at point B. So our kinetic energy at point B is going to be found by the gravitational potential energy that he lost at the beginning, so from A to B, but we've got to take away the work done due to friction. So often we presume there's no friction and we say that the kinetic energy is just going to be the gravitational potential energy, but this question has specifically told us how much friction there is because we've just worked it out. So we're just going to pop in our numbers. So this was in part A, the gravitational potential energy, and it was 90,000 or 90 kilojoules. So it was 90,000 joules, and we're going to take away the work done due to friction, which we just calculated, 20,000 joules. So it is 70,000 joules is our kinetic energy of the skier at point B. For D, the skier is brought to rest at sea due to resistive forces that at between B and C determine the work done. So we do know at B, they've got a kinetic energy of 70,000 joules, but by the time we get to C, they're not moving, so the kinetic energy equals 0. So that means all of that energy, that 70,000 joules, has gone and turned into thermal energy, which is the work done by the resistive forces. So this is actually your answer, 70,000 joules. Question 5a. A crane is used to lift a steel beam of mass 750 kilograms as shown in figure 1. The crane raises the beam vertically upwards at a constant speed of 0.5 meters per second. Part A, calculate the upward force produced by the crane required to raise the beam. So we are just going to do force is mass times gravity here. So the force required is going to be 750, so that's the mass times gravity, so it's going to be 7357.5 newtons because it is a force. 5b, calculate the power. For this, we are going to use the equation power is equal to force times the speed. So we're going to do that number that we've just worked out, 7357.5, times the speed in the question, 0.5, and the answer you'll get is 3678.75 watts. I've got the 5 in there, 75 watts, or roughly 3,700 watts. Question 5c, the beam is raised through a vertical height of 15 meters, calculate the work done. So we're going to use work done is equal to the force times the distance. So the force we got from part 1, I believe, so it's 7357.5, and we're going to times it by that 15 meters that we've got there, and we're going to get 110,362.5 joules, or if we give it to two significant figures, just 110,000 joules. Question 5d, the crane is supplied with 5 kilowatts of power, calculate the efficiency. So to do efficiency, we can do the power out divided by the power in times 100 because we want to give it as a percentage. So our power out is going to be from the previous page, part B, this number, 3,678.75 watts, and the power in is in this question, 5 kilowatts, 5,000. These are both in watts, and then we times it by 100 so we can make it into a percentage, and you get roughly 74%.